today we'll see the nth root of unity. Okay, so we have already discussed that if you find the nth root of any complex number, let's say z complex number rho, I have to find the nth root of unity. So how was the process? So we convert into Euler form. So it's 1 by n modulus e to the power I 2 pi k plus alpha by n, where alpha is the argument of complex number rho, of which the nth root of is to be determined, and here the k values varies from 0, 1 to up to n minus 1. That is, it will give the corresponding n roots. Okay. Now, in case of nth root of unity, this complex number is nothing but 1. So z will be 1. So if rho is 1, okay. So rho is 1. So obviously the argument of rho, that is 1, is nothing but 0. So for nth root of unity, let's say nth root of unity, for nth root of unity, we are finding the nth root of unity. Okay, we'll write this as a z as 1, that is e to the power I. So clearly here alpha is 0 because the argument of 1 is 0. So 0 plus 2k pi by n, or I can say e to the power I 2k pi by n. Okay, now substituting different values of k, we will get the roots. So here clearly the k values is 0, 1, 2 up to n minus 1. Okay, so let's see. So if I say nth root of unity e to the power I 2k pi by n, if I substitute z, let's say if I substitute k is equal to 0, z1 is e to the power 0 is equal to 1. If I take k is equal to 1, the second root will be e to the power 2k pi. So it will be, second root will be e to the power I 2 pi by n. Similarly, if I substitute k is equals to 2, the third root will be e to the power I 4 pi by n, and so on. So let's say the last root, if I substitute n minus 1, the nth root will be e to the power I 2 pi n minus 1 divided by n. This is the nth root. And considering, so this value, let's say this value is alpha, so obviously this is alpha square, okay, because 4, no? So basically if alpha is 2, alpha is e to the power I 2 pi by n, so alpha square is nothing but e to the power I 4 pi by n. Okay, so it goes like this, 1 alpha square. Similarly this will be alpha to the power n minus 1. Okay, so this z 1 by n root has roots. What are the roots? Roots are, I can say 1 e to the power I 2 pi by n e to the power I 4 pi by n e to the power I 6 pi by n, and up to e to the power I 2 pi n minus 1 by n. Okay, and these are called, let's say 1 alpha square, alpha cube, up to alpha to the power n minus 1. So if you're replacing with e to the power I 2 pi by n alpha, so it will be alpha square, alpha cube, alpha by n. One important thing is, see, these are the n roots. These are the n roots. Clearly, if you solve any, let's say z to the power n is equal to 1, we have to find the nth root of unity that correspond with the z to the power n minus 1, 0. So this is nothing but the nth degree polynomial. Since n degree polynomial, therefore we are expecting the n roots, and that's why we have this 1 alpha square, alpha cube. These are the n roots. Okay, so now we have discussed the roots, so let's discuss about the properties. So before properties, see, we have discussed the nth root of z is equal to 1 to the power n. The roots are 1 alpha square, alpha cube, up to alpha n minus 1. These are the roots. Clearly root seems to be in GP. Okay, roots, no, 1 alpha alpha square roots in GP with the common ratio as alpha. Alpha means e to the power I 2 pi by n. And if we convert into the trigonometric form, we'll see that the alpha is nothing but e to the power I 2 pi by n. So at any stage you can convert into the trigonometric form, that is cos of 2 pi by n plus I sine 2 pi by n. Okay, so alpha square alpha cube, we can easily find the corresponding value by converting into a trigonometric form. Okay, see, let's talk about some properties of this nth root of unity. So let's talk about the properties of nth root of unity. Okay, so what are the properties of nth root of unity? So basically, since we already discussed last time that when you're talking about the nth root of any complex number, so all the properties which we discussed in case of nth root of any complex number here also were valid. Only thing is here the row has been, the particular complex number is now a 1. Okay, so what are the properties associated with this particular nth root of unity? Obviously first we see that the roots are in GP. So what are the roots? So clearly roots are 1 alpha, alpha square, alpha cube, alpha to the power n minus 1, where alpha is e to the power I 2 pi by n. So first property is obviously roots will be in GP. Okay, we can clearly see roots in GP. So roots in GP with common ratio as e to the power I 2 pi by n, with the alpha, that is 2 pi by n. And second root is, if we talk about the difference of arguments, so if we draw this complex number on the Argand plane. Okay, so let's draw in Argand plane. So they are basically mod z, so basically z is equal to 1 to the power 1 by n. So the locus on which if taking the modulus, the locus on which the roots will lie on the circle. Okay, so we can see that the roots, so we can say the roots lie on circle with center origin. The center is the origin, this is the real axis, and this is the imaginary axis. The roots lie on a circle with center origin, and radius is 1. So basically the circle will have a radius is 1. So basically the radius of this circle is 1. Okay, so what are the roots? The roots will be, one root is here. Okay, this is the roots, that value is 1. No, we can clearly say 1. Then other root will be alpha here, then other root will be alpha square, and then alpha cube, and so on. Okay, and if we talk about what is the alpha, so alpha is, see, alpha has the value e to the power I 2 pi by n, that is the complex number with argument is 2 pi by n. That alpha square has argument e to the power I 4 pi by n, that is the argument is 4 pi by n, this value is 4 pi by n. So what is this corresponding? This value will be 2 pi by n. Same way alpha cube will have a value 6 pi by n. Okay, so this value 6 pi. So what is this difference? That is 2 pi by n. Got it? So the difference of arguments between the two roots will be 2 pi by n. Got it? So we can say that the difference of argument, the fourth difference of argument between the roots, between two roots will be 2 pi by n. Okay. And okay, this thing. Next thing is we can see that, okay, okay, so next talk about the, if you look at this particular, if you look at the this particular circle, we observe, just observe on the circle one important thing. Let's say this is first root, this is, let's say, alpha is the second root, that is e to the power I 2 pi by n, and if it was the last root, that is alpha to the power n minus 1, that is e to the power I 2 pi n minus 1 by n. And if you clearly solve, we get e to the power I 2 pi into e to the power I minus 2 pi by n. So e to the power I 2 pi by is nothing but cos 2 pi plus I sin 2 pi, they turn out to be a 1. So ultimately alpha is nothing but e to the power minus I 2 pi by n. Got it? So if this angle, this argument is 2 pi by n, the argument of the last root is minus 2 pi by n. So they are just, and since they are lying on the circle, so clearly alpha to the power n minus nothing but the, they are nothing but the conjugate, complex conjugate. Okay, so clearly we can see that the conjugate pairs. Got it? So basically we can here observe that the roots, the imaginary roots exist in conjugate pair. Okay, so if real root is fine, real root will lie only on the x-axis, but the imaginary roots, if a complex roots, they will lie in a conjugate pair. Same way we can talk about the alpha square. Let's, so okay, so let's say we can clearly see here also. Let's say this is alpha square, and the last, so this is alpha square, this is alpha n minus 1, this is alpha n minus 2. Okay, so we can clearly see if alpha square is what, e to the power I 4 pi by n, and what is alpha to the power n minus 1, e to the power I 2 pi by n minus 2. Simplifying it, you will get I to e to the power I 2 pi into e to the power minus 4 pi by n I. So this value is clearly 1. So we will get e to the power minus 4 pi by n I. So if this is any complex number, this one alpha square, so this is nothing but the conjugate of alpha square. Okay, so what I mean to say that the roots lie on the imaginary roots lie on the conjugate pair. Okay, ठीक है. Okay, so next, let's say the next property is I don't know which property. ठीक है. So I can say here the alpha is conjugate of, or we can say the last root, alpha to the power n minus 1 is the conjugate, alpha to the power n minus 2 is alpha square conjugate, and so on. Okay, okay. The next property is, we can say the, so next property we can say sum of roots. Okay, sum of roots will be 0. Okay, let's say the roots are 1 alpha square alpha cube up to alpha n minus 1. The sum of roots will be 0. So we can say either this is nothing but 1 plus alpha square plus alpha cube up to alpha n minus 1. They are in GP. So GP means common ratio alpha, number of terms n minus 1 upon alpha minus 1. Clearly here, what is alpha n? Since alpha is alpha n means e to the power I 2 pi by n, this is nothing but e to the power 2 pi, that is 1. So this is 1 minus 1 0, sum of roots is 0. Okay, we can also observe that since this is the roots of z to the power n minus 1. Okay, so sum of roots means sum of roots is also also 0, because the coefficient of z to the power n minus 1 is 0. No, sum of roots is coefficient of n minus 1 divided by the coefficient of z to the power n. So clearly here the coefficient of z to the power n minus 1 is 0. Then also we can say the sum of roots is 0. Okay, so now talk about the next property. So clearly see, alpha to the power n is equal to 1 we have observed here, and alpha square to the power n, that is also 1, because ultimately there are two ways. See, they are the roots of z to the power minus is equal to 1. So z is equal to 1, alpha square, alpha cube, alpha to the power n minus 1. They are the roots of z to the power n minus 1. So they will satisfy. Satisfy means it's either substitute. So z is equal to alpha, or so z is equal to alpha or alpha square or alpha, whatever we substitute here, they are going to satisfy this equation. So alpha square will also satisfy, alpha to the power q is also satisfy. Satisfy means alpha cube to the power n minus 1 0. That's why whatever the roots we substitute 1 or alpha q, they are going to be a 0. Okay. Next point is, we can say, since the alpha to the power whatever value, let's say alpha r, the modulus is 1. Since modulus is 1, or we can say value of this is 1, so we can say that the roots are unimodular. So roots are unimodular. Roots are unimodular. The word, so we can unimodular. Roots are unimodular. Why roots are unimodular? Because the value of the modulus of the root are 1. Okay. So one key observation also with the whenever some say unimodular. Okay. So let's talk about unimodular. When we say unimodular. So unimodular means z magnitude is 1, or we can say z square is equal to 1. We have discussed z square means z of z bar is equal to 1, or whenever any complex number is unimodular, then z is equal to 1 by z bar. Okay, or z bar is equal to 1 by z. That's the interesting things in case of a unimodular. Okay. Since I am saying that the roots are unimodular, that means alpha is same as 1 upon alpha bar, or alpha square is same as 1 upon alpha square bar. Okay, and so on. Or we can say any general alpha k is same as 1 upon alpha alpha k same as 1 upon alpha k bar. Okay, that means alpha to the power n minus 1 is 1 upon alpha to the power n minus bar. Okay, because roots are unimodular. Okay, and okay, then next point we can say we already discussed that. See, they are also conjugate pair. So alpha n minus 1 is alpha bar. Okay, alpha n minus 2 is equal to alpha square bar. We have also proved this thing, that is they occur in conjugate pair. Got it? And this is alpha 1 by alpha, and alpha square is 1 upon alpha square. Okay, so this is how these relations we can use solve some problem where alpha to the power n minus 1 is alpha bar, because they are conjugate pair, and since roots are unimodular, hence alpha bar is nothing but 1 by alpha. Same way, let's say alpha to the power 3 is alpha to the power n minus 3. Okay, so we can say this nothing but 1 upon alpha n minus 3 bar. Okay, and also this is also same as 1 upon alpha 3 bar. Okay, so in this way we can solve some of the problem where we use. See, we can also observe by this one. If I say alpha to the power n minus 1, this is alpha bar. We have proved using the geometry in the previous slides. We can also say that alpha to the power n minus 1 is alpha to the power n upon alpha, and alpha to the power n is this is 1. No, because see, why 1? Because z to the power n is equal to 1. So z will be 1, alpha, they will satisfy. So alpha to the power n will be 1. So this is alpha to the power 1 is equal to 1 divided by alpha, and 1 by alpha is nothing but alpha bar. So in that way also we can prove that alpha to the power n minus 1 is alpha bar. Okay. Okay. Then let's take the let's say the next point. So see, the things are roots. Roots are symmetrically placed on circle. The important thing is roots are symmetrically placed on circle. What does it mean? See, if I say z to the power n is equal to 1, so surely one thing, surely one root is sure. So one root will be 1. Okay, and since roots are symmetrically placed, so other remaining roots will be symmetrically placed. For example, one root always be 1, other roots we have to place symmetrically. For example, if I say z to the power 4 is equal to 1, since roots has to be symmetrically placed, okay, roots are symmetrically placed, roots are symmetrically placed. So I can say that let's draw the roots. So they lie on a circle with center as origin and radius is 1. So one of the roots, so clearly one of the roots is here. This is one of the roots. Okay, that means 1 is the root. Other roots are symmetrically placed. So other root will be here, that is -1, then here I, and here -I. Okay, so they are symmetrically placed. So I can say roots are 1, -1, I, and -I. Okay, roots has to be symmetrically placed. For example, if I also observe, let's say z to the power 6 is equal to 1. Okay, z to the power 6 is equal to 1. So again the roots, one of, since one root is 1, we are sure. Achha, by the way, you should know that if z to the power n is equal to 1, if n is even, so 1 and -1 are the roots. Okay, surely. And if n is odd, then only 1 will root, only 1. No, will not, no -1. So in case of even, 1 and -1 is the root, and if it is odd, n is odd, only 1 is the root. So that is important. Now since here z to the power 6 is equal to 1, so obviously we can the roots. So clearly 2 roots, we know that this is 1 and this is -1. Now remaining roots, the remaining 4 has to be symmetrically placed. Okay, symmetrically placed. So what happens? How do we divide symmetrically? So best method is first find what is the alpha value. So here alpha, since this is one root, other root is alpha. So alpha is e to the power I 2 pi by 6 or e to the power I pi by 3. So clearly this pi by 3. So this is alpha. Okay, and has to be symmetrically placed. Okay, this is pi by 3. The other root will be the alpha, that is 2. This is again 2 pi by 3. Okay, since we know 2 roots, we need 2 more roots. They are symmetrically placed. If this root is, let's say this root is z2, here also the bar z2 bar, that is pi by 3 conjugate, there is the last root will be here, let's say 5. Okay, or let's say 5th root. Similarly, this is the first root, this is the 3rd root, this is the 4th root, symmetrically placed. This is this 5th root and 6th root. So if this angle 2 pi by, so this is pi by 3. So again this is also minus pi by 3. So this also symmetrically, z3 and z4 are symmetrically placed. So what I mean to say that z5 is nothing but z3 bar, just like z6. Z6 is nothing but z2 bar, which we have discussed before, that the roots are in conjugate pair. Okay, so if I have to find what are the corresponding roots, okay, so we can find the corresponding roots. So one of the root is here 1, so one root is 1, other root is let's say -1. These are the two, 1 and -1. Now this root let's say this roots, this is pi by 3. Okay, so what is the third root is e to the power I 2 pi by 3, that is e to the e to the power 2 pi by 6, so it will be pi by 3. So essentially it will turn out to be a cos of pi by 3 plus I sin pi by 3. So that means cos pi by 3 1 by 2 plus root 3 by 2i. Okay, this is the full root. Then since this root, we have here also one root exists. Okay, conjugate pair. So other root will be 7. Let's say this is first root, this is second root, this is third root, this is fourth root. Fourth just a conjugate pair. So minus. So conjugate pair means z3 bar, that is minus half minus root 3 by 2i. Now next root will be here z4. Okay, z4 we already assume, fifth root, z5. So this is pi by 3, and we know that the difference, no? Since it is the, what is the difference argument between the two, the difference of argument between two roots is 2 pi by n. So clearly here is a 2 pi by 6, that is pi by 6. So difference is pi by, so this is pi by 6. So what is z fifth root? E to the power I, the argument is pi by this is pi by 3, this is pi by, so it will be I 2 pi by 3. Okay, so that means it is cos of 2 pi by 3 plus I sin 2 pi by 3. So cos 2 pi by 3 will be, what is the value? Minus half plus root 3 I by 2. Okay, so and what about this sixth root? Sixth root is same. Sixth root is the z5 conjugate, that is minus half minus root 3 by 2i. Got it? So this is how we can find the fifth root, all the six roots. Okay, now if I talk about, let's say this one, z to the power 5 is equal to 1. Since z to the power 5 is equal to 1, we know that one of the root is 1. One of the root is 1. But since this is odd, 5 odd, so minus 1 will not be a root. Okay, first root is 1, and we have to see where other roots lie. So we know that where is the first root? This is alpha. So what is this argument? 2 pi. So what is the difference between argument? What is the difference of argument between two roots? 1 and alpha. So that is 2 pi by n. Clearly pi 2 pi by 5. Okay, so this is 2 pi by 5. This roots, and this is the roots. We have the next root also, alpha to the power n minus 1, 4. Okay, so that is alpha bar, that is this root is e to the power I 2 pi by 5. This root will be e to the power minus I 2 pi by 5. Okay, first root we got 3 roots. We need 2 more roots. So 2 pi by 5, the other root will be here. The difference between the argument is 2 pi by 5. So that is alpha, let's say square. Okay, so alpha square value will be e to the power I argument 2 pi by 5 plus 2 pi by 5. It will be 4 pi by 5. 4 pi by 5. So this root is here, and where next root? Conjugate pair. So this is alpha 3, that nothing but alpha 2 bar. Okay, so what is the alpha 3 value? Is bar, we can directly say e to the power minus I 4 pi by 5. So what are the roots? One root is this one. So I can say first root is 1. Second root is alpha, that is e to the power I 2 pi by 5. Third root is this one, alpha square, that is e to the power minus plus 4 pi by 5. And what is the fourth root? Fourth root is the conjugate of alpha square, that is alpha square conjugate e to the power minus 4 pi by 5. And what is the fifth root? Fifth root is conjugate of, fifth root is here, conjugate of alpha, that is alpha bar, that is e to the power minus 2 pi by 5. This is how we find all the roots of a complex number. Okay, so So you should, this important things, whenever we get z to the power n minus 1 is 0, you should note that when n is even, then roots will be 1 and minus. This will be help to determine other roots, because we already know 1 and minus 1. And if n is odd, then only 1 is root, okay, not the minus 1. Minus 1 will not be a root. Okay, now let's talk about some of the other important properties. Let's say the other important properties. See, whenever we say 1 plus alpha square plus alpha cube up to alpha n minus 1 is 0. So see, the alpha they may be a complex number, that is it has the imaginary part as well. So right hand side is the 0, right hand side pure 0, and left hand side has a mixed part. So since right hand side is 0, obviously left hand side should also be 0. If left hand side 0, that means clearly the real part, the left real, so we can say that the real part of left hand side will be 0, and the imaginary part of left hand side should be 0. Both left imaginary and real part are 0, then only we can say the right hand side is 0. Okay, so what is the real part of, if you talk about the real part of left hand side, so real part of left hand side, I can say 1 plus alpha square. So alpha means e to the power I 2 pi by n, e to the power I 4 pi by n, up to e to the power I n minus 1 pi by n will be 0. Okay, so if you talking just the real part, so 1 is real anyway. E to the power I 2 pi by n means cos of 2 pi by n plus cos of 4 pi by n up to cos of n minus 1 2 pi by n, they will be 0. Okay, so real part means this part is 0. Got it? This is the real part of this one. So essentially we know that this is very important result. Also we can say 1 plus cos of 2 pi by n plus cos of 4 pi by n plus cos of 6 pi by n cos of 2 pi n minus 1 by n 0. So this is the one of the identity we study in trigonometry, okay, which we can easily prove using the complex number. Okay, there are many trigonometric properties we can prove with the complex number, we have shown in the previous lectures. Okay, same way if you talk about the imaginary part is 0, if the imaginary part of 1 plus I 2 pi by n plus e to the power I 4 pi by n up to e to the power I n minus 1 pi by n is equal to 0. So imaginary part means 1 is not the imaginary, only the sign will be the imaginary part. So we can say that the sine of 2 pi by n plus sine 4 pi by n up to sine n minus 1 pi by n is equal to 0. Okay, so these are the things. Let's take one very basic example. So if someone asks you what is the value of the cos of 2 pi by 11 plus cos of 4 pi by 11 up to, let's say, cos of 20 pi by 11. Okay, what is this one? So clearly if it's last, if here n is equal to 11, so what is n minus 1 to n minus 1? Basically pi by n, pi by everywhere. So only new thing is, okay, one more thing. Here 2 I miss multiplying the 2. This is 2. 2 is also multiplied here. So this is 2 is also multiplied here. So 2n minus 1. Okay. So 2n minus 1 is 20. So clearly it shows that we know that 1 upon cos of 2 pi by 11 plus cos of 4 pi by 11 up to cos of 20 pi by 11 is 0. But we are asking only this value. So corresponding answer will be minus 1. This minus 1 goes right hand side, they become minus 1. So the answer of this particular question is minus 1. Okay. So one more property, very interesting property. See, z to the power n minus 1 0 has roots 1 alpha square up to alpha to the power n minus 1. So I can write like this: z n minus 1 is equal to z minus 1 z minus alpha z minus alpha square up to z minus alpha n minus 1. Okay. Now this is valid for whatever you substitute, they are valid. So I can say substitute anything. Let z is equal to a. So we can a to the power n minus 1, a minus 1, a minus alpha, a minus alpha square, a minus alpha to the power n minus 1, satisfying for any values of a. Now one interesting thing is that, let's say we use this formula, this one, x to the power n minus 1. We know that this is x minus 1, x n minus 1, x n minus 2 up to 1. Now, if we simplify, simple, this is algebraic identity. So substituting this x to the power n is the algebraic identity. We assuming x is equals to z, the z to the power n minus 1 will be z minus 1, z n minus 1 plus z n minus 2 up to z square plus z plus 1. Okay. Now z to the power n minus 1 is z minus 1, z to the power n minus 1, this one, and the corresponding root form is also z minus 1, z minus alpha n minus 1. So we can say that since z n minus 1 is equal to z minus 1, z minus alpha square up to z minus alpha to the power n minus 1, and z n minus 1 is nothing but z minus 1 and z n minus 1 plus z n minus 2 up to z square plus z plus 1, and that is same as this one. So z minus 1 and z minus 1, these getting cancelled, I will get a very important identity, that is z to the power n minus 1, z to the power n minus 2 up to z plus 1 is nothing but z minus alpha square up to z minus alpha n minus 1. That is a very interesting result. Okay. What does it mean? It means the roots, important roots. So the interesting thing is that means the roots of equation z n minus 1 plus z n minus 2 up z plus 1 is equal to 0. Roots of this are what? Alpha square, alpha cube up to alpha n minus 1, where alpha is e to the power I 2 pi by n. Mind is n, it's not 2 pi n minus 1, because this is the part of z to the power n minus 1. So where alpha is e to the power I 2 pi by n. So if you want to find the roots of any polynomial equation with this form, has the roots alpha square, alpha cube, alpha to the power n minus 1. Okay. So for example, let's try to solve one problem. Let's say we have to find the roots of this 1 plus x square plus x cube is equal to 0. This is currently, this is basically this is a form of x cube plus x square plus x plus, all the forms are present. Okay. So basically all the terms of cubic with the coefficient, so basically all the terms of polynomial is present, cubic, square, 1 and constant, and the coefficient is 1. So I can say this is nothing, the roots will be the roots. So if you want, I can write like this: 1 plus x square plus x cube is equal, roots will be x minus alpha square, x minus alpha cube. Okay. And what is alpha here? E to the power I 2 pi by 4. Okay. That means we have to find the 4 roots. And we have discussed in the previous slides that z to the power 4, they lie is equal to 0. So what are the roots? They occurs at 1, minus 1, I and minus I. So directly we can say this corresponding roots will be 1, minus 1, I and minus I. These are the roots of the equation 1 plus x square plus x cube is equal to 1. Okay. So so we can say that the interesting thing, if we have any polynomial of x r, or let's say write like this, any polynomial, let's say x to the power m plus x to the power m minus 1, x to the power m minus 2 up to x plus 1 is equal to 0. So first of all, this is a polynomial of degree m and coefficient of all the terms is equal to 1, and is a complete polynomial. Complete polynomial means all the terms are present. All the terms are present. Okay. Then what are the roots? Roots will be alpha square up to the power alpha m. Okay. And what is alpha? E to the power I 2 pi upon m plus 1. Got it? M plus 1. It's a m degree, so m plus 1. That is the things. Okay.